welcome back. We're going to continue our discussion on electronic configuration for elements in row 4 and beyond. Okay, so this is basically our domain 2, okay, which deals with elements in row 4 and beyond. Okay, all right, that said, the following rules only apply to elements in the 4th row and onwards. And if you see a couple of rows or a couple of rules in this set of rules, it's exactly similar to the rules in domain 1, because some of it is essentially the same, but there's a couple that distinguishes on explaining the why that we put forward. All right, so first write the orbital sequence. Okay, just like you would do for any element, you would write the orbital sequence. Okay, you take it for its face value. All right, now I will underline and point out where you will make a mistake. All right, so I mean, I'm telling you where you will make a mistake, so if you know that, then you can fix it. Or remember, hey, he mentioned you will make a mistake here, so just focus on that. All right, fill electrons in each orbital left to right, keeping in mind how much maximum an orbital can hold. Well, it doesn't seem like it's new. Well, it's exactly the same thing. In fact, I copied and pasted the first two rules, so this is exactly the same. And this is where things get tricky. Again, make sure you don't overfill the last orbital in the sequence. Always make sure the electron count matches the atomic number. So the first three are in fact exact same. All right, so here's the problem. Shuffle the orbitals so that all orbitals with 3s are with 3s, 4s with 4s. And that might be a statement. Without further visual example, it will make literally no sense to any of you that are watching this video. All right, so shuffle the orbitals. So you don't shuffle until you actually meet the first 3 requirements. So essentially you must do exactly everything right like you did for domain 1, which is where you will stop for domain 1. So you must get the first 3 right before you shuffle. Do not shuffle while you are filling, or shuffle and then follow rule 1, 2, and 3. No, it will be wrong. Okay, now after you shuffle and finish up, that's when you actually end up with the correct electronic configuration. Until you shuffle and then verify everything is right, you cannot be too sure that you don't have the correct electronic configuration. Now let me explain this, the reasoning why I'm doing it this way. The textbook does not do it this way. It has a very more conventional way of teaching this subject, and I don't think, if it is not explained in this way, I think the chances or probability of number of students getting this idea right is very low. Okay, this seems like easy for people that get it, but for people that find it hard, even this level of chemistry could be very, very hard. Okay, so that's what I'm trying to explain to you. All right, so let's take an example. Okay, what do I mean by putting 3s with 3s, 4s with 4s, etc., etc.? Right, this is the key. This and then the shuffle, and then what I have underlined here. These are very, very key, and this is exactly where things can go haywire and probably go wrong. All right, so we have titanium. Okay, where is this titanium in the periodic table? You have to look at the embedded view that I have shown. All right, well, it's in the 3D band, right? So what do we have to do? Okay, I'm going to actually ask the question. Well, you have to find the electron count, total electron count. So atomic number is 22. So how many electrons does Ti have? 22. So I'll leave this on because the reason I'm doing that is, all right, so our first we have to write the orbital sequence. So it's 1s, and then we have 2s, 2p, 3s, 3p, 4s, and 3d. All right, you have to follow the sequence just like the rule says, and start filling electrons up until the last one. Just leave it blank and then count and then subtract and fill that one out just like we did earlier. S can hold 2, S can hold 2, P can hold 6, S can hold 2, P can hold 6, S can hold 2. Stop, just like we did earlier. If you count, that's 10, 12, 18, 20, right? So we have 20 at this point, right? We have 22 total. So 22 minus 20 is 2, and we put 2 here, okay? So we have now successfully done the 2, and we also made sure we didn't overfill by doing this extra step, and always make sure the total, this is 22 now, which is equal to 22. So we have taken care of 3. Now here's the thing, all right? Things can get a little bit more complicated as we go to the next row, that is 5th row. But the rules are the same. This, if you follow these rules, you will have no problem. Now, what do I mean by 3s with 3, 4s with 4s? In this case, there is no other 4s, but when you get to row 5, you will have another 4. But what we're really trying to interested is move this 3D here and move the 4s here. So the 3D will be with its family. Don't put the 3D all the way in front of the 3s, because the energy order is S followed by P followed by D followed by F. Okay, that's the energy sequence. So D cannot be in between S and P, or it cannot be in front of S. So all you have to do now is write everything back. Don't change the electron count, okay, just because you're moving it. You're just displacing the whole thing in front, and that's it. Now, this is not the way I have seen it being done. Okay, when I learned it, or when I've seen it being taught, this is the correct electronic configuration. Okay. Now, normally it's written directly, and that leads to an enormous amount of confusion on understanding the material. This is very easy. All right. So let's go ahead and put these up, see if I did my thing right. Ooh, okay, there we go. Do I do it right? Oh yeah, I did right. Well, why did I even doubt myself? Now I get it right. All right, so let's look at maybe one more example without actually, making things. Maybe let's do, RB, okay? Okay. Rubidium. All right, rubidium is in the 5th band, 5s band, right? So we got to start writing everything up until that point. 1s, 2s, 2p, 3s, 3p, 4s, 3d, right? And then 4p. You have to write the sequence as they appear, okay? And 5s. That's where we stop. Now fill everything except the last one. So 2, S can hold 2, P can hold 6, S can hold 2, P can hold 6, S can hold 2, D can hold 10, P can hold 6, and then count everything, see how much you need to get this done. Rubidium's atomic number is 37, so we have 37 total electrons. So if I count this, this is 10, 12, 18, 20, 30, 36, right? That means I'm left with 37 minus 36 is 1. So I've completed rules 1, 2, and 3 for domain 2, right? Now what I mean by is 3s with 3s, 4s with 4s, 5s with 5s. There's no other 5, so first let's move the 3s to stay with the 3. So this goes over here, this goes over here. Well, now 4 is with the 4, right? And then 5 doesn't move anywhere because we don't have any ways to move it. So if you see now, when I write the final sequence, it all makes sense, right? Everybody is in their respective 3 family, right? Right? No one is in any other family but with their own family. What I mean by that is, you see the 1s is by itself, the 2s are with 2s, the 3s are with 3s, 4s are with 4s, and the 5s are with 5s. If there's another 5, what I mean. This is the correct electronic configuration that we are looking for. Does that make sense? All right. So what I'm going to leave you with here is, I want you to practice this, okay? Just practice these, and then when we have our live session, or if you do it in class, then you can ask questions about it. All right. So that's how you do the regular free flow electronic configuration. All right. So stay tuned for the valence, the discussion on valence orbitals, electrons, condensed electronic configuration, and boxed electronic configuration.